Hi, everyone. My name's Dan, and nice to meet you. This can be hands-on, or it can just be like it's up to you. Like I was going to give like a very simple, easy to sort of do, watch, and do at the same time workshop on doing a whole bunch of compute using your own device, like a compute cluster made instantaneously of your own devices. So maybe I'll just do a little blah 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 first, and then if there's interest in doing the follow along, we'll take a break, and then we'll just go back interactive, and then maybe Justin can do the relay through Discord of any links that give you head starts on stuff. So, anyway, quick background. My name is Dan Desjardins. Um, Background as a military pilot. I flew the big C-130s for search and rescue for many years. That was a lot of fun. My dream as a child was to become an astronaut, and I worked really hard my whole life to do that. So that's why I went into aviation and so on and so forth. Did my PhD at Queen's University. Undergrad, master's, and PhD were all in space science and physics. The PhD focused in computational electromagnetics and theory. And the whole goal was to look at force interactions between electromagnetic coils and conducting tubular structures, because you can put vehicles inside tubular structures, as you know. And so the idea is if you can use electromagnetism to create your own levitation and your own propulsion inside these connecting tubes, then you wouldn't need motors or moving parts or transmission gearboxes or anything else. So that's what I was all nerdy about when I was doing my PhD, and still beyond. It's still a passion project. I'm helping master's students now. But yeah, we do the math that explains what these levitation and propulsion curves are going to look like. And so I'm going to show you a little bit of it without going into super gory detail, or we can go into super gory detail if you want. So maybe we'll make it a democratic vote. And then I'll talk a little bit about the compute that makes this type of innovation possible, and then bridge to sort of what we've done now, which is so I left the military and I became a professor and a researcher. And in doing a lot of this compute, I needed more of the computing power. And so started a startup 4.5 years ago, and we built a platform that essentially takes all the idle computers in a university and turns them into like a giant supercluster to do compute. It's not Kubernetes or Docker or VMs under the hood. It's actually pure web tech, and so we'll get into that. Are there any questions right off the bat, or shall I just dive right in?
So currently Justin's not here right now, so I don't know. For me, do any of y'all have questions?
No, yeah, let's just keep going.
Yeah, absolutely. So I'm currently I'm Shivali. I'm with the PNS at CHC. So um, Justin will be back in a second. But basically, we've been listening very intensely, and we have our laptops ready. So
Okay, cool. Well, I'll do some primer context so that we don't just jump into straight up compute, because that's less connected to the Hyperloop stuff that you're all doing. So I'll just show you sort of like my own personal this mini deck I made a long time ago to show some of my own researchers and colleagues at the Royal Military College of Canada um, what I was up to and why, sort of like the science, and then we can do the compute stuff. So this has got to be one of the nicest renderings of a futuristic Hyperloop train or whatnot that I've seen. And so naturally, I stole it for my presentation. And it sort of shows the elements. It has some good ones and some bad ones, and I'll talk about that. So in this, it's clearly a metal tube. It's not a nice see-through glass one, other than the cutaway that they gave us so we can see the actual thing on the inside. But the rest of it, you can see it's sort of like a metal, probably aluminum, as it's lighter, tubular structure. It's circular, of course, and it's suspended by those sort of Y-shaped things. And you can see this Hyperloop capsule, or the vehicle itself, is riding on like a sort of superconducting linear track. And that's how it's obviously I mean, that's where it sort of connects to everything else, and it levitates and floats and moves along. So just remember that, and then I'll come back to that. Wouldn't it be cool if we replaced our rusting Via Rail trains with a sweet Hyperloop that went from Montreal to Toronto, and of course here it's missing Kingston on the map, but we would make sure that stop gets added. Maybe goes a bit beyond to Waterloo. Wouldn't that be nice? And maybe a little bit east to Quebec City, and then we have the whole corridor. That would be nice, Kingston to Toronto in 20 minutes would be pretty sweet. And people have actually been working on this. Like this is back in 2018. There's actually a Canadian Hyperloop company working on this kind of stuff, and they threatened to relocate if the government wasn't more supportive of this type of innovation. Now, of course, the government's trying to do the best they can, but pandemics and wars and everything else seem to get in the way quite often these days. So what we have is on the left, what we'd like is on the right. How do we get there? And so this is where I come in, I put my nerd glasses on, I say, okay, well, just for fun, my research was all about if you drive a voltage through an electromagnetic coil, you set up a current, obviously. But that current creates a magnetic field, and that magnetic field, as it's impinging upon its conducting surroundings, will induce eddy currents within the nearby metals. And those eddy currents will create counter-magnetic fields that induce counter currents in the primary coil in the first place. So that sort of feedback interaction sets up forces which can levitate and create drag and everything else. And we can also look at not just the conducting structures, but even ferromagnetic conducting structures like steel. Because steel will do two things. One, because it's a conductor, it's a metal, you'll induce eddy currents in it. Now, everyone here, if you remember your electromag courses, if you've taken a little bit of that, you should have, I think, in your core curriculum, you'll know that conductors will, if you put a changing magnetic field near them, you'll induce eddy currents, via induction. And Maxwell's equations describe that. But if you have ferromagnetic materials, that magnetic field will also magnetize those materials and will enhance magnetic flux. And if you enhance flux, you're also magnifying the induced currents. That's getting quite complicated. So when you have steel, ferromagnetic conducting steel, you have simultaneous magnetization and eddy current induction effects. And those enhance and focus flux, and all that creates feedback back on the loop. How the hell, sorry, pardon my language, but can you imagine coming up with the math equations that describe all of those complex phenomena? And so this is sort of what it would look like. So imagine if you have either one or a caterpillar, like an array of these coils that are essentially pulsing an alternating current going between, where you're reversing the polarity of the current at some hertz, some frequency. And simultaneously, that coil is moving with velocity v down that conducting tube. So by now, you can see we're sort of setting up what this Hyperloop sort of thing could look like. So that was what I set off to do, is to solve the equations to figure out what the force felt by this coil would be for a coil that's pulsing at a certain frequency and moving at a certain velocity as it's traveling down a certain tube with certain dimensions and thicknesses of the inner and outer structures and different conductivities and different magnetic permeabilities and so on and so forth. Why? Because it'd be nice to be able to minimize drag and increase levitation and everything else. So this is a very sort of simple 30,000 foot up view on the different things that you can calculate. So obviously the forces are of interest. So the force that's felt by the electromagnetic coil is given by the current density in the coil with cross product with the curl of the magnetic vector potential in that region where the vector potential is created by that's reflected by the tube structure itself, which means we're going to have to go and solve this thing by solving a boundary value problem. But we can also go and get other interesting things like the electrical impedance and even calculate the induced current density within the walls of the Hyperloop tube itself. This is what it looks like a little bit more expanded out. This will give us axial force, which gives us drag felt by the coil. Now, you all know that superconducting maglev trains, the faster they go, the less drag is felt, right? So we're hoping to see that when we plot the math here. We also plot the induced currents to see what's happening inside the metal itself. So here's what happens when we actually run a bunch of compute on those equations. So at 0 hertz, so literally just a straight up magnet, a static magnet that's moving at a certain velocity. Velocity here is in the x-axis, and the drag that you see in the y-axis is the force, the counter force felt by the coil. So you can see for a static magnet or electromagnet moving down the tube, drag is going to increase as velocity increases, which is what you'd expect. Like as you're driving down the 401, the faster you go, the more drag your car is going to feel. But wait a minute, at some point, you actually hit a maximum and then drag decreases again. And in fact, the faster you go, the more drag decreases. And this is why maglev is so awesome, is because the faster you go, the less magnetic drag you feel. You'll still feel air resistance, which will still increase as in a quadratic form, but at least the magnetic drag is disappearing, which makes sense because there's less, because if you're going faster, the magnetic field has less time to penetrate the conductors, which means the skin effect occurs over a thinner region, which means that losses are less and blah, 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 blah. But something pretty crazy happens when you start to say, well, instead of considering a static magnetic field, what if you invert its polarity some number of times per second? So essentially now, instead of running a DC current through the coil, you run an AC current. So at 100 hertz, we've actually killed a lot of that drag. Isn't that crazy? And 200 hertz, you're killing more, and 500 hertz and 1000 hertz. And I took the time to draw this line of 0 drag to make very obvious that these curves are dipping below 0 drag. What does that mean? Well, we're actually going into negative drag, which is actually thrust. Holy shit. So we're not violating conservation of momentum or energy here. There's no UFO technology built in, I promise. Like you definitely are, like energy from the currents and the coils are definitely being induced into the pipe. So you are pumping power into this thing to make it go. So at least it's not violating thermodynamics as it shouldn't, because otherwise we could just end this call right now and you can call me a charlatan. But let's take a look at what's happening when we're in a drag situation and when we're in a thrust situation. This is the other equation I was talking about, where we can actually calculate and show what the currents are doing inside the metal boundary itself. So in a higher drag scenario, as the coil turns on, let's say, the field in a certain direction, it's inducing a cushion of currents. But and it's obviously moving, that's why there's a lot of asymmetry. But then these currents, the bow shock, the wake is weirdly migrating to become a bow shock, and so on, and it sort of comes around it like this, right? So there's a recirculation of vortice of the induced current densities. Now yellow is going into the board, so to speak, and blue is coming out of the board, and obviously they're reverting like in out because the current is going in out, right? But look what happens in this thrust region. So look, 16 meters per second and 500 hertz. I'm going to go back here. So 500 hertz, 16 meters per second is right about here. So this is we're in the negative drag or the thrust regime. So in this, you can see what's happening. The coil is inducing a cushion of currents, but it's ever so slightly lagging behind the coil because the coil is moving. But by the time the coil reverses its polarity, we've sort of suppressed the recirculation, and it's pushing on the cushion of currents it just created behind it. Think about that. The coil induces a cushion of currents behind it, and then the coil reverses its polarity because it's at 500 hertz, 500 times per second. So the coil creates a cushion of currents, and then it reverses its polarity, and then it pushes on the cushion of currents that's lagging behind it. And then it induces the opposite polarity of currents, but then it reverses its own polarity again. So it continuously generates a wave of currents behind it and then pushes on that wave. Now, of course, it's not, like I said, it's not stealing energy here. Like the currents that it's setting up in the metal, or like the power being dissipated by those currents, are coming from the coil itself. So you're not getting anything free here. So it's totally physically. This is totally in the realm of classical physics. So it's totally real, totally true effect. Nothing made up here. But that's interesting. It's kind of like a surfer that creates its own wave behind it and continuously surfs its own wave. But obviously, it takes energy to do that. So this coil obviously has a giant battery pack or something going on for it to be able to do that. But what's cool is that there's no motor here. There's no gears. There's no grease. There's no wheels. It's purely driving a current at a specific frequency through an electromagnetic coil, and it's creating its own cushion of currents that it's riding smoothly and quietly down this tube. So that sort of concludes sort of the physics and some of the cool stuff about my research. But I'm going to like to pause there and just ask questions about the science, because the science is cool. Then I'll get into the compute aspects. Anyone want to turn that into a discussion?
I don't know. I think we're still kind of, surprised at the research. It's a lot to take in, all at once. It's very interesting though. So, like, my only question is, how did you even know that you were interested in this? How did you even?
That's good. Eh? It was accident. Well, okay. Well, first of all, how can you not be interested in like space elevators and maglev and hyperloops and all this kind of stuff? Right? It's the same technology as railguns as well, right? It's all this futuristic, state of the art. Nothing's touching sort of magnetic fields. I mean, that's how we control plasmas now. And that's how we want to achieve nuclear fusion and all this other good stuff. And the tokamak nuclear reactors and so on and so forth. So a lot of cool stuff to do with electromag. But it originally started when I was choosing a master's thesis topic, and I was on my way to be a military pilot. So I had to choose a thesis topic that was portable in case I got called early to go to pilot training. So I could not choose a thesis topic that required a wind tunnel or equipment that I couldn't bring with me. So I chose something that's a little bit more theory, because I can take a pen and a bunch of paper with me, to go to Moose Jaw, Saskatchewan, and I could have finished sort of my thesis without having access to a wind tunnel, because all I needed in a more theory-based master's would just be pen and paper. So that's one of the reasons why I did a more theory-based thesis. And of course, it had to be physics, because that's what I did my undergrad in. So theory-based master's thesis in physics had to be theoretical. So that sort of limits you to astrophysics and astronomy. But what scared me about that is, as cool as it is, like we can all agree, black hole mergers and all this stuff is like super cool. But it's the jobs available afterwards are mostly in teaching astronomy, or if you're lucky, working with some of the big telescopes and doing, like, what I mean? It's like anyone can learn to play guitar, but only a few of them actually can break away. Same with astrophysics and astronomy. Like there's a lot of people taking it because it's friggin' cool, but there are only so many radio telescopes and observatories around the world. So getting a job in it in a really applied way is difficult. So then your only backup to that is then teaching in a university. Or you go out into industry and say, well, if I can calculate the mass of a black hole, I can probably model like the stock market and then go work for a bank, right? So, which we've seen a lot of. So, I mean, if you're doing astrophysics, you're smart no matter what. It's sort of like the thinking. Same with engineering and any other non-arts program. No offense. Obviously, I'm talking to engineers, so I feel safe making that joke. At least I hope. And apologies if there's someone with a history major in the class right now. You shouldn't be doing hyperloops. Anyway, I can't tell if you're laughing behind that mask. So I got into eddy current non-destructive testing. So using magnetic fields to test whether pipes were corroded or pitted or breaking or cracked or anything else, without having to remove paint or cement or whatever coating there is, or insulation or foam or whatnot. And that's used a lot in the oil and gas industry, right? But it's also, if you've seen the figure eights, it's how we inject current into the brain and measure sort of like things, with like transcranial stimulation and stuff like that. So there's, using these magnetic fields all over the place. And then for my PhD, I just took that to the next level, and I solved something called the feedback problem, which allowed me to do a lot of fancy stuff. And then beyond the PhD, actually, as a hobby project, This is when I went from just calculating impedances and signals and currents and all that, to actually calculating forces, which all I had to do is take the cross product of current density and the vector potentials that I already learned how to solve for, and voila, now I'm doing forces, and that's infinitely more interesting because that opens up maglev trains and hyperloops and rail guns and space elevators and all that kind of cool stuff. So that was a long-winded answer for how I ended up in this. So it was sort of like a series of early strategic decisions with respect to compatibility with career and mobility and everything else, but also being like applicable technology, and because it opened up careers, unlike astrophysics, which is hella cool, but less directly applicable to jobs on Earth. And then after that, I just became interested in continuing the research. Now, obviously, as a pilot, I was paid to fly planes, which gave me all the flexibility in the world to pursue some of this research on the side. Actually, if you can see my screen, I've been helping a master's student, and I showed her how to solve some of these math problems. And she sent me this yesterday. And what you're seeing is the magnetic field with respect to distance away from the center of a coil. And what you actually see is theory and experiment. Do you see the two lines? They are literally on top of each other. And she accused me of doing witchcraft. And because the theory, the math is so good. And here's the other one. Again, this is theory and experiment. Just you can see the two curves there, the blue and orange. So it's literally witchcraft, and it's intoxicating, right? The notion that you can do. And I'm going to show you. And I'm going to go back to showing my screen. I'll show you what some of this math looks like. I'll show you. It's totally intoxicating to feel like you can understand and model nature, understand it, and so on and so forth. Let's see. So mirrored. Well, something like this. I realize we're not doing any coding right now, but let me know if you want me to shut up on the science, and we'll get into the. Hey, look, and I use maple, a product of Waterloo, so that should hit close to home.
I mean, to be honest, we're just interested in hearing you speak. Anything you could teach us is valuable. So.
Thank you. Thank you. Okay, so this is what the students working on. They built these rectangular cross-section coils, electromagnetic coils that you'll inject current through above conducting and ferromagnetic plate. And the idea is, as you drive a current through these coils, it'll induce currents in the plate, and those currents will depend on the thickness and the permeability and the conductivity and the liftoff and all these other characteristics. So by measuring the signal you receive, you can characterize the sample, and that's even if you're not touching it, at a distance, which is pretty cool. I just went an extra step, and I said, okay, let's make the coils move, and let's calculate forces. So that's the only difference between this and sort of the stuff I was just showing in that presentation. But the math here, and I'm not going to bother to go to like, I don't want anyone to get any nosebleeds here, and that's not the point. But I do want to show you the elegant complexity of it. Like, we're doing triple integration over kz, ky, kx from 0 to infinity essentially, and somehow these things are giving answers that are exactly matching experiments. So this is telling us that the inductance, the self-inductance of one of those rectangular coils is 17 millihenries, and the answer was 16.95, the experimental. So it's ridiculous. Like, can you think about that? Like, we're literally, this is a three-dimensional function that we have to integrate. We have to integrate its volume in like Fourier K-space, and it can give any number, complex number between minus infinity and plus infinity, and it gives you exactly within 1% the experimental value. It's wild. That's what I find most fun and satisfying. Like, it just makes you feel so good. Anyway, so once we can do that math, now we're getting into, this is see if you recognize this is the theoretical predicted vector potential in the y direction. And she went and got the measured and compared the two, and it was perfect. Here's what it looks like if you were to do it like 2 dimensions all at once. See, lighting, none. So it's pretty, eh? Like, I just like the colors. It's cool. Of course, these are 3-dimensional, so if I move it around, you can Anyway, same for the AX, same for the AX. Then we can get into really some really cool stuff. So this is the vector field of the currents induced as viewed from above. So you can see it's all circulating. You're inducing currents in the plate, and they're all circulating around where the coil kind of is. And then to take it really to the next step, and then we'll get into the compute soon. Now we can also do the magnetic flux density in XYZ, and calculating this takes a lot of compute power and a lot of time. Like, by the way, like I'm showing you the finished product of the computations. It actually takes like hours and hours to do to run all the compute. And that's what I'm actually building up to here. This is a fisheye view of the magnetic field existing everywhere in the plate below those two coils. And you can kind of see here the coil is injecting flux, and then it's popping out over here, right? It's kind of cool. So if there's a crack in this plate, it would disrupt the flow of flux. And that's how you can sort of measure the effect of cracks and things without touching anything. And the math keeps going and keeps going. And now here's the sort of like the most awesome part of it all. This is actually a 3D animation. This is let me make it go in a loop. These are the currents being induced in the coil. And you can kind of see that as they're strong at the surface, and as you get deeper down, they get weaker. And you can see that they're even lagging, right? See how they're slightly like behind, anyway, so there's that underdamped oscillation, if you will. So it's just cool. All this comes from all that math. And what else? This is data visualization overload, And then okay, so but of course I can't see what's happening inside a sample. Thought I had another one for the magnetic field. Anyway, these are examples of oscilloscope signals that you could measure with an electromagnetic coil that was above a sample. And so this gets compared to experiment again, and you can show that these are all theory. So this is what the student's doing now. She's collecting oscilloscope signals with and without the presence of a plate. So the green signal here is the voltage. The yellow is the current, and you can see the current is lagging the voltage because of the self-inductance of the coils themselves. And then the red line is the coils next to a plate. So clearly the presence of the plate is modifying the shape of the signal. So that's the sensing going on right now. So she collects experimental data by taking her air core coils and putting them next to the plate, and it matches. Well, Bob's your uncle. Now we have more theory and experimental comparisons. Okay, so I'm going to stop there. Is there any questions on maybe the science or even if you have personal questions to me, I'm happy to share that too before we get into some compute.
We have a question.
So with all of your research on electromagnetism and induction, I was wondering, what are your thoughts on linear induction motors and using the feasibility of using those for hyperloop?
Yeah, excellent question. What I haven't done yet, I haven't pushed this research to its limits, because I've been showing sort of how you can create thrusts, right, by sort of perfectly choosing the right frequency at the right velocity to sort of ride your own cushion of currents. But what we haven't talked about is, well, how big is that thrust, right? Because if it's only like a micronewton and it's giving you like 0.1 meter per second squared acceleration, then it's not really usable in real life. So what I haven't done yet is do the optimization. So now that I have the math, I'd like to look at, okay, well, what's the right size and dimension of coil, right? Should it be long and thin? Should it be thin and narrow? Should it be thick? Or should I have three of them in series, offset by some phase difference? And what are the forces in all those situations? So now we're going to get into the compute side. So essentially there's like a 15-dimensional, like one for each parameter. So the length of the coil is one dimension. The inner radius of the coil is a second dimension. The outer radius is a third dimension. The thickness of the first layer of the tube is another dimension. The conductivity, the electrical conductivity of the tube, the first layer of the tube is another dimension. The magnetic permeability of the first layer of the tube is another dimension. Then you get another 3 for the outer tube. And so very quickly, when you add all these up, there are 13 dimensions that you can, or parameters you can play with to calculate. Oh, and then frequency and velocity are there, right? So there are 13 parameters inputs that you can tweak in order to calculate a force. So in terms of a hyperparameter optimization problem, we would have to search a 13-dimensional space for maximal thrust to weight ratios to figure out what that maximum thrust to weight ratio is. And once you have it, then we would know if it's useful from an engineering point of view. Does it give you a usable thrust, or is it like an academic, it's just cool academically, like it's like a fridge magnet with a thrust, right? So that's a good question. Linear induction motors, I think, well, this is essentially a linear induction motor, but across like the whole ring instead of just on a track. So they're actually they're the same. It's the same physics at play. It's just one is taking advantage of the whole ring, like the whole electromagnetic coil in the ring or circle will interact with the whole tube, whereas the linear induction motor, it's just like a bottom piece below it. So, but it's the same physics. So what are my thoughts on it? More inconclusive, more research is required, which is a typical academic answer, I think. Okay, so, go ahead, Justin, you're gonna say something?
So I guess, is there any more questions here? Because I guess you were taking some Q&A time.
Yeah. Well, we were just exploring some of the science before because I figured it's more relevant to talk about the Hyperloop stuff with a Hyperloop crowd than to talk about like maybe just a pure straight up compute. By now, we've been 35 minutes out of the hour on the science and all that, which I think is applicable. And if people want, I can start now diving into how I actually ran these computations. So right now, what you saw in Maple, the math formulas, I can show you some of the compute that goes into actually turning those equations into plots and knowledge and looking for these optimal parameters that create these thrust to weight ratios and so on and so forth. Okay, before I jump in, anyone else curious about anything about the science or even like personal journey or anything else?
So far, no one. No.
Okay, good. That's what I like to hear. I'm just getting all the questions. Okay, so screen share. Now I'm going to do something a little wild. I'm going to use everyone's computers that they're working at right now to run some of these computations. No download, no install. So what I just brought up here is it's just a JS Fiddle. It's in-browser IDE, which is what and for those who are familiar with coding, IDE is sort of like your environment that you write and execute code in. So VS Code is an example of a native IDE. This is an example of a web IDE, which is kind of cool because you don't have to download anything. It's just literally just type a link and boom, you're writing and executing code. This tab shows all of my math. So I know none of you were kind of looking really closely at the math I was showing, but there were interesting things like hyperbolic Bessel functions and Bessel functions and so on and so forth. So everything here, all of this code is just the code version of the equations I was showing you earlier in Maple. So I just typed out a bunch of code. And towards the bottom of all this horrible stuff, but you got to admit it's pretty neat. I take great pleasure in making things look clean and modular. We get down to, so I'm looking for the axial force felt by the coil. And these are like the 12-dimensional inputs I was talking about. So force, velocity, current, number turn density of the coil, the, I forget what this is, length of the, the width of the coil, the length of the coil, the resistance, the this, the that, and everything else. Conductivity, permeability, width, conductivity, permeability of the tubes. So that's the axial force. So this is performing numerical integration on all the functions you just saw. So that takes a lot of compute. And I do it again for the radial force. So radial force is levitation, and axial force is levitation of that coil. I'm gonna run this twice. This is showing you the actual code, and then I'm gonna show you a pretty front end that sort of hides it, makes it pretty, and does plots instead. So going back to the main page, this is the workshop I gave at a computing workshop not too long ago. Today, obviously, I focus more on the science and less on the compute, which I'm doing now. But in the computing workshops, I focus more on the compute. This is what we like to show off. One single line of code exposes the client library, the DCP client library. And DCP stands for Distributed Compute Protocol. And what that means is, hey, take my compute, my problem, spread it over a bunch of computers that are in the libraries and wherever on the campus, and get me my results faster. And so that's our goal, or that was my selfish goal, is, hey, how can I take my calculations and spread them over more computers and get the results back faster? Because if I'm sitting around waiting for hours or days for my computations to happen, I'm doing nothing. So we want to accelerate innovation. One line of code gives you the DCP client library. After that, this here is just, we use this symbol instead of typing this over and over again. So that's just to avoid typing that over and over again. This is a multi-range object, which is essentially an array of arrays for the hyperparameters I was telling you about. And so this is the main function that we're going to execute. And I only need like 6 ingredients: an input set, a work function, compute.for, compute groups, and I'm going to call execute. So my input set is a multi-range object, which I declared up here, or I made available up here. I required it. And this is where I'm saying which frequencies, 100 hertz, 200 hertz, 500 hertz, 1000 hertz, which velocities, which wire turn densities, coil thicknesses, coil lengths, la, 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 la. So I'm going to essentially calculate results for each and every one of these data points that I want computed. This is just a very nice, neat, compact way of expressing it. So for all 4 of these frequencies, calculate all of these velocities for all of these parameters. So if I were to unroll this object, this range object, there's a couple of thousand computational points to perform. And if each takes a second, well, that's a couple of thousand seconds. That adds up. And of course, if I increase these and I made them all range parameters, I'd quickly have more points to calculate than there are particles in the universe, which would take 100 billion years to complete. And I'm not even kidding when I'm saying that. We're actually working on a project right now for a Laurier researcher that's going to take about 100 billion years to complete on a laptop. We're now spreading it across all the laptops in the world, and I'll more on that in a second. This is just a simple demo. So anyway, my input set. It's all the input parameters I want to run compute on. Then I want to define a work function, and you guessed it, that work function is the axial force and radial force functions that I showed you in the other tab. So I'm going to apply all that math I wrote to some arguments. And the arguments, of course, are going to be the input set. And I'm returning these 4 things: frequency, velocity, axial force, and radial force. Now I'm saying, okay, well, my computational job is dcp.compute.for, the work function, which I obviously defined here, applied to every element in the input set, which I put up here, in parallel. And that's it. So this is essentially a parallel for loop, or a glorified version of map, for those of you who know what that is. So we're just mapping the work function onto each element in the input set. The input set can consist of billions of entries, you know what I mean? So if you were to actually run this job on one computer, it would take quite a long time. But if you spread it out and spread it across all the computers at Laurier that are doing nothing all summer, you have essentially a supercomputer at your fingertips. I'm requiring the math packages and the tube forces packages. I'm giving it a cute name called Dan's Physics Job, and I might even say Dan's, you can even call it Waterloo Job, because we're all a bunch of Waterloo folks today. And I'm going to put it into my private compute group. called Dan with password DCP. And these are just some events that say, hey, whenever, when the job, when the ready state changes, so uploading job, deploying job, something, like just show me the status changes. And this one, whenever a result comes in, show me the result. And then I just call execute on the job handle. And when it's done, tell me something. So it's going to say, may the force be with you. So anyone have any questions on what is a very trivial way to express a frigging gigantic computational workload? Like this can consist of billions of inputs to search. This is all of my physics code. Obviously, it's like the actual physics code is behind this function, which is written somewhere else. Parallel for loop that's going to map the work function onto each of the elements of the input set. Requirements, give it a name, dump it in a private compute group. I can also put it in a public compute group if I want. If I deleted this, it'll go to the DCP public network made up of computers all over the world. But here I'm deliberately putting it in a private compute group, and it can be multiple private compute groups because I want it to be just your computers today working on it. So I'm going to reprime the pump. Okay, run. So that's loaded. This down here, this is what, and okay, of course, the bottom part, like these things, these are just HTML divs. So there's and buttons and stuff like that. So this code here creates what you see down here. And so it's going to dump the results into these divs that I mentioned here in the ready state changes and the result events. So I'm going to say deploy. And it wants me to say, well, you got to pay with your compute credits. So I'm going to pay with my Portal 2 account. And by pay, I'm going to tell you about the compute credits. It's a bank of computing power. If you do work for the network, you get paid. If you deploy work to the network, then you spend. But it's free if you give as much as you get. Sharing economy of compute power. And it's for Dan's Waterloo job. And so I say, yes. So the job is already deployed. That took like a fraction of a second. But notice nothing's happening right now because there are no compute nodes in the Dan compute group. So this is where I need the audience's help to be a cheap magician right now. I need you all on any device, whether it's your phone or your laptop or an iPad or a vacuum cleaner. And later I'll show you a picture of us doing this on a fridge. And I'm not even kidding. Open dcp.work, W-O-R-K, /Dan. So this is in any browser. Chrome, Safari, Firefox, whatever. DCP, that's Delta Charlie Papa, .work /Dan, and the password is DCP, all lowercase. If everyone's done that, you'll see the DCP web worker, and then hit start. And what you should see is it should say going out and looking for work, and as it retrieves slices, it's computing them. And if you can look at my screen, I'm already getting results back. Isn't that crazy? And so I didn't lift a finger here. This is being computed by one of your or a couple of your computers in the room right now. Securely, might I add. It's as secure as online banking because it's built on the same web standards. So there we go. With just a single click, we made a compute cluster made up of all your devices. If some of you didn't get any work, it's because someone else was quicker than you and they snatched it all up and they did it. For bigger jobs, the workload would distribute across all available devices. Any questions on what we just did there?
No, so far. None so far.
Cool. And I got my message, may the force. So there we go. We got all the results back. It's kind of cool. I all used your devices. No need for cloud here. I didn't spend a dime on cloud, nor did I spend a week trying to set up a stupid container or an instance on the Azure or AWS or EC2 Spot. Or like what? All we did was dcp.work/Dan. Boom, instant compute cluster to do arbitrary code and compute to accelerate science and innovation. Isn't that cool? I think it's cool. a little side description before, and then we're going to go and build our own stuff. I have some REPLs that will be easy to share and sort of experiment with here in a second. But one last note on those compute credits that I was talking about, spending and earning. Some of you probably see like that you've earned some compute credits. Let me go back. So for those who didn't run it, I'm going to show you. vSpeed.work actually makes you join like the public network. vSpeed.work / something makes you join the something private compute group. So if I just go into the public compute group, you can see I'm fetching slices. And it says working because it went and grabbed some computational workload from the public network. And as it completes it, it's going to give me some compute credits. And it's paying into this bank account. Now you're all wondering, what is this bank account? Well, because you didn't initialize it, it's mine. But if you were to actually go set up a DCP account and see the settings tab up here, you can actually change that bank account and it would be paying you instead of paying me, which is not a not smart thing to do. Or it's a smart thing to do. I shouldn't use double negatives there. And then when you accumulate these credits, there's two things you can do. One is obviously cash them out for money because compute power has a value. And it's all PayPal in the background. This is not a cryptocurrency, just putting it out there. Or more importantly and more usefully, you can turn around, you can spend them to run your own computational workloads. So what we've done essentially is we've created a compute battery where when you're doing work for other people at night or whatever, you either run the browser or better yet, run the screensaver for Windows computers, which is up here. Or you can just run or whatever, and then you accumulate these compute credits, and then when you need a crap ton of compute, well, you can burst all at once across 1 million computers and just do things a lot faster. So you can see I'm going to be rich here soon. What does that look like? So if I go to the portal itself, this is what my portal looks like when I log in. That's the welcome screen. If I go to accounts, you can see I have a whole bunch here, but this is my key store where I have a couple of compute credits in it. And so I can transfer credits, I can spend them, I can do all kinds of things. So when I do work, I'm replenishing this. When I'm launching work, I'm spending from it. And as long as I'm giving as much as I'm getting, it's a free compute network. It just enforces fairness. Those who don't want to give and just want to get, that's fine, but then they have to buy those compute credits. And those who just do work and don't need to deploy any, they can withdraw cash. That functionality is coming soon, like sort of this summer. It's not there yet because we've been sort of secretive about this whole project. We'll be launching a public network where people can use it. And when that money starts to come in and out, that's when the economy, if you will, boots up. But for the time being, it's kind of cool. We're deploying this on campuses and in hospitals and stuff like that. So I'm showing you a lot of stuff right now. Justin, I'm going to send you a link to share with folks.
Okay, got it. Nice.
So this replit, let me put it in the chat. So that replit, before you open it, I'll just show you what is there. There's only, I think, 4 examples. So I'm slowly doing this. It doesn't exist yet. We have compute API examples. That's to write and launch jobs, like my physics job I just showed you, though the physics one was a bit more complicated. And then I have 2 web worker examples where you can set up the compute cluster side of it, right? So one is the deploy job and the other one is compute a job. So I'm going to show you the web worker example first, and then you can have fun in modifying. I don't know if there are web developers in the group here. Obviously, I'm showing you very web-centric applications just because it's so easy to share and work with, but we also have Jupyter notebooks and Colab files and Node and even Python scripts and whatever you can imagine. So I'm going to open the public network REPL. Oh, that's not what I wanted to do. I want to edit it. How do I do that? Edit. Because I want to show you what's under the hood here. So this, because the REPL is available, you can fork it and you can change it to your heart's content. So here in this REPL, there are only like 5 lines of code that are important. The rest is just for show. Notice this this script tag here. This is the same script tag that exposes DCP client to your web application. And then these lines of code instantiate a DCP worker within that page. And that worker will pay into this address. So make sure when you fork this to make it your own address so you don't pay me. And it will set up this number of threads, or what we call sandboxes, safe execution environments for code. And that's it. That's the instantiation of the worker. And then you just call worker.start, and that's it. Now you have a working worker inside this web page that's running this many parallel slices, job slices, and when it's earning credits, it's paying them into this account. And then everything down here, these are just events, and I'm displaying them in the HTML document as these events come in. So this is all optional stuff. And then I have in the body, I just say, hey, here's a minimal worker, happy computing, so on and so forth. So I'll show you what happens when you run this. And by now you've probably guessed this is exactly what you just ran. Like you just ran a pretty one, the dcp.work/Dan. That's just this, but made pretty by us. People can make their own workers, and they can make it purple, and they can make it Waterloo themed, and they can embed it in a news website. They can embed it in literally any web page in the world. In fact, if I were to embed these 3 main lines of code in the New York Times, every computer in the world, as they're reading the New York Times, would suddenly be working on my network. Think about that. If we embedded this in Google's HTML, obviously we don't have access to Google's HTML document, but if that was in the Google landing page, we would have like 600 million computers doing compute for us live. So anyway, so let's run this. So if I run this page, look, it showed me what it should because it was built there. And you can see here, it's pushing events to my screen. It says fetching job slices. Okay. It's within 30 seconds, it will have gone to get a whole bunch of work. Actually here doing work. Okay, 60 slices have been fetched, and now it's computing. So all this is happening in the background on my computer. If I was to pull up system resources right now, you'd see that my CPUs are pegged at 100%. And we can also use GPU and a bunch of other stuff. So that's sort of in a nutshell, with 3 lines of code, how you can embed a worker into any web page on Earth and turn every computer browsing that page into a compute cluster node. And look, I'm getting rich here. So this you can fork, and you can make it look like whatever you want. But that's essentially how you set up compute clusters. Any questions on the worker REPL example? So this example, it went and fetched, and as you can see, it keeps going here forever. It's fetching from the public network. If you want to make a private worker run from a private repo, just go to the other one. So this is the DCP browser worker in a compute group. So if I open this one, it's actually identical, except for there are 2 extra lines of code. One makes it leave the public group, and another line of code makes it join 1 or more private compute groups. So if I wanted, I could put my Dan compute group. Now these compute groups, you don't get to create them. We create them. So you have to use pre-existing ones or request that we create one for you. So for example, we could create one called Waterloo. If there was enough interest from Waterloo computing folks, we could create a Waterloo compute group. Otherwise, these compute groups are real and they exist, and you can use them. Feel free. Okay, any questions and everything else is the same. Any questions on this? I'm going to stop sharing and take a pause before going back to the how to deploy work.
So far, still none. I think, yeah, so far I don't see anyone.
Okay, no questions. How about feedback? What do people think?
Yeah, some of them are saying it's pretty impressive. It looks pretty good.
Well, thanks. No, that's super appreciated, because we're just so excited about this too. And maybe I'll show you one more thing here. where we've pushed this to an absurd, like we just did a crazy demonstration of it running on Twitch just because we could.
Oh, you're getting some claps.
No.
A lot of claps. So yeah.
Well, let me show you. Okay, sharing my screen. Okay, so check this out. This is me and co-founder. 4 years later, we got it working on a fridge. This fridge is doing computational physics. Have any of you ever seen a fridge do computational physics?
No one here has seen it before.
So, so we can run this on cars, fridges, watches, phones, tablets. We literally aggregate the computing power of every device and any device on the planet, running any operating system, any hardware type, like anywhere, anything, and no download and no install. Like think about that. Just dcp.org/mygroup, and you instantly have your own compute cluster. Okay, and so maybe I'll conclude with the other side, which is just like the API stuff. So if I go back to this, these are the compute API examples. 2 uppercase is a really trivial, cool example, so I'll open that. So in this is another version of this. Okay, so this shows the API, how you write jobs and deploy them to those compute groups that you just created. And I see I'm almost out for time here, so if you have something to go through, we can sort of pause. This would be a natural breaking point where I could stop if you have to be somewhere else. It's your call, Justin.
Give me a second. Yeah, I think it's almost time because right now we have like a little break, and then there will be more stuff after.
Yeah.
So I think
Let's end it. Let's end it.
Yeah.
So let's wrap it up.
Yeah, it's a really good presentation.
No, I'm super happy. Thank you very much. You're great, and I'm very happy to redo this anytime anyone wants and share and show more. And if people want to play with it, experiment with it, let me know, and we'll hook you up with compute credits and compute cluster, and we'll help you debug or whatever. Like we like feedback, so it's all good.
Yeah,
thank you.
No problem. So yeah, we're gonna share with everyone the link you put in chat, and we're also going to share this workshop with people that weren't able to attend this, as they might have had another workshop they want to go to, or they had their interview. But in the future, they'll definitely have you back, as I think this is a very informative and very great workshop. So is that the email you put in?
Yep, I just replicate importantly Mux communication is how things work. More importantly, is my email. Of course, feel free, anyone, if you want to connect on LinkedIn. I'm a super connector. I'm happy to chat with anyone. So if there's any questions or anything whatsoever, again, we love when people play around with this stuff and tell us what can be improved so we can continuously make it better. And what we really want to do is set up a compute cluster at Waterloo. So if you know of a computer science professor that needs compute, connect them with me, and I'll get them set up.
Yeah, for sure. And we definitely have, I think, a lot of interested people, but they might have not been able to make it. So, and I think, and I'll put your LinkedIn when I post all this later, because we're going to send a recap at the end of the day to people to recap what has happened. And I'll put this recording plus the links and your LinkedIn as well, to make sure that anyone that's interested can reach out to you for more assistance or questions.
Very cool. If that recording is available on YouTube, I'll rebroadcast it too on the social media.
Yeah, I just have to talk with my YouTube, my photography and videography lead, and she'll handle that and let me know. I'll let you know when it's available.
Absolutely. Thank you so much.
Yeah, no problem.
Bye.